Okay, wonderful. Okay, great. Yeah, thank you so much for that introduction. I'm really excited to be here talking with you all today. I really enjoyed the earlier talks and keynote as well. So yeah, my name's Alison Smith-Renner. I am a research scientist at Dataminr, where I design, build, and evaluate human AI interactions for augmenting human workflows. My research interests are right at the intersection of HCI and AI. In fact, for my PhD, I had two advisors. This is not totally rare, but I had one in HCI specifically and one in deep in machine learning. And so I really have been kind of working in this space for a long time, and it's nice to see it growing and more people getting behind this sort of human-centered focus for machine learning. So a lot of the work that I'm going to talk to you about today was completed during my PhD at University of Maryland. And specifically, I'm going to talk about human-centered design, or designing for the human in the loop, for machine learning. And I'll talk about when user control can have unpredictable effects in machine learning updates, and kind of how users perceive and react to this. So as everyone knows, machine learning-based systems are becoming increasingly prevalent in our day-to-day lives. So this includes everything from virtual assistants, movie recommendations, or more critical settings like medical decision support tools. And in general, humans are increasingly wanting and needing to interact with machine learning. So such interactions might occur for assessing models, like determining whether they're accurate or have any bias, determining whether to follow or ignore recommendations that are given by a system, or iteratively providing feedback to adapt or improve models. And in particular, I really focus on two critical aspects of human interaction with machine learning, which is how systems explain their inner workings or justify their predictions to users, which we can call transparency, and also how users can provide feedback or guide systems or control. So just for a little bit of background, explanations in machine learning are techniques for systems to be understood by humans. So contrasting this with more black box approaches, where we might be able to view system outputs, perhaps assess their performance in some way, but we don't really get any insight into how they work. Explainability is important, or like, why is it important to ask why? It's important because we need to know more about systems than just their accuracy. We also need to know how and why they make predictions or perform actions. And this lets us support understanding both where models work well, but also importantly, their limitations. So this in turn increases appropriate trust in systems. We can also ensure that our models can generalize to other domains appropriately and are operating without bias. And what does explainability look like? So explanations can be local or post hoc explanations that justify particular decisions, like on the left. So this explanation for a interactive or a text classification system that determines whether emails are about hockey or baseball. An explanation can show the prediction by the model that it's baseball, as well as some confidence score, here 90%. And then the explanation is the highlighted words that led to the classification of that class. So we're highlighting words that led the model to predict that this document is about baseball. On the other hand, we can expose more global or model transparency. So this visualization of a decision tree, which was trained to differentiate home location, determining whether homes are from New York City or San Francisco, based on different features. So it's really hard to read this chart, but at the top, the first decision point is based on elevation. So most homes in San Francisco are at higher elevation than New York City. So we drop in the decision tree and can go, if it has a higher elevation, now we are more likely to predict New York City or San Francisco, and we can keep going down these decision points. So this gives a global explanation of the model, and it's, you can probably guess, is more useful for pretty simple models like decision trees that are easy to visualize and understand. So significant prior work has explored the effects of explanations for various desired human AI interactions with some mixed results. So explanations can help to increase understanding of how models work and the errors they make, to increase users' mental models can also yield better feedback for interactive machine learning. So I actually think this was touched on at the end of the previous keynote, but for the reinforcement learning context, but it is the case for supervised interactive machine learning, where the more users understand how the model works, the better feedback they can provide, especially if the explanation form is the form that they provide the feedback in. So that's an interesting kind of insight going forward when we build these types of systems. Explanations can also help to support fairness and bias assessments. On the other side, they can lead to inappropriate trust, in some cases over or under reliance. Users sometimes overtrust systems just based off the explanation, particularly if it's visual explanation that looks really good or has a lot of math in it, and they just have more trust for the system by just providing that explanation. And then additionally, users can have decreased perception of systems when the explanations expose uncertainty. Finally, in some of our prior work, we showed that explanations can also increase users' frustration when they expose errors, but without opportunity to fix those mistakes. So when we don't pair explanations with feedback mechanisms or control, that can be problematic. So another important theme of human interaction with machine learning is control, or the ability of the user to change, adapt, or influence the machine learning system, which of course we all know about because that's the theme of this workshop. But control enables personalization or customization through preferences and general improvements or overcoming errors through iterative feedback loops. So this talk, I'm focusing on a particular case of control or feedback in machine learning, which is called interactive machine learning. So in this case, a human in the loop iteratively improves or adapts a model. And compared to classical machine learning, interactive machine learning has more rapid, focused, and incremental model updates, which are led by user interaction. So in this figure, which is adapted from the human AI group at Stanford, the idea is that the system provides some intermediate feedback. A not fully trained system can show some examples or some outputs and say something like, how do you like it so far? And then our human in the loop can perform interaction or curation to say, not bad, but more like this, or these particular examples are what I expect, or I would prefer to see examples like this. And then this feedback is immediately incorporated to improve the system. And this iteration continues until the model is of high enough quality or the user is just happy enough with how it looks or doesn't want to interact anymore. So I see in the comment, human controls machine learning or machine learning controls human. That's kind of an important question of this is sort of what level of agency does the human have, does the machine have? Is there this possible teaming relationship where the two work together? In most of my work, we try to have the human has has the most control. The system might also have a large amount of control, but not more than the human has. So we're trying to make it so the human is controlling the ML with allowing the ML to have agency as well. So I'll get to that a little bit more as well later. So let's take a look at some examples of interactive machine learning. So this first example is from the Crayon system at Fels and Olson. It's actually the first time anyone used the term interactive machine learning, at least in a paper, and it was in 2003. So looking at this figure from the left, for the first iteration, users draw on an image to help a classifier distinguish the foreground from the background for a segmentation task. So starting from the left, the input data, users draw on what they think is the foreground. They draw separately on the background. That information goes into the classifier, which performs an initial segmentation. It does okay, misses some of the mistakes, some of the foreground or background for foreground in some cases, and vice versa here, thinking that the foreground is background. So the user can continue iterating, providing additional training inputs to help kind of fix those exposed errors. You can see in the next version, we get a little bit better, but we still have some issues in certain places, which the user can then fix with their next drawing. And then by the end, we get a pretty decent segmentation over just a few iterations of input. And then another kind of common example is in interactive text classification, which is a supervised machine learning case. Here we have a model that was trained on hockey or baseball labeled emails. So we have tons of emails either labeled as whether about hockey or baseball. The model learns an initial kind of understanding of these emails based on the words and phrases that are contained within. And then this tool is called Dualist by Settles. I think someone else was talking about some of the Settles work earlier, but Dualist, in this tool, users can iteratively train the model to better distinguish hockey and baseball emails based on interacting with intermediate output. So they can provide two forms of feedback. They can either provide instance level feedback where they're correcting or confirming system predictions. So for example, we see this email and that it's been labeled as being about hockey. The user can either confirm that label or change the label to baseball. They can also provide feature level feedback, which is a richer form of feedback where they can specify words that are more likely to be about hockey or baseball. So beyond just correcting the system or providing additional training labels, they can provide more information for the system to go on in the form of the words that it should sort of pay attention to for each of these classes. And then there's even more commonplace examples of interactive machine learning, like personalization, for example, Pandora, where users thumbs up or down songs to get better recommendations. So like with transparency, control has both positive and negative effects, or it can have them. Interactive machine learning methods can yield higher quality models, but can also lead to decreased system performance. And control lets users personalize models and create models that better align with their understanding of the data, but also requires significant user investment and cognitive effort and time. So that was just to give a little background on transparency and control in interactive machine learning, which is kind of the space that I've been in for a while, but this is specifically a talk about designing for the human in the loop for interactive machine learning, meaning to take a human-centered design approach. So what do we mean by that? So AI systems are often designed from an algorithmic-centric view. So this means that system developers optimize for system performance, sometimes at the expense of user experience, or they design interactions based on how they think that end users will want to use these tools, which results in systems that are not trusted or accepted by end users and a gap in our understanding of end user experience with machine learning. But human-centered AI is a research area that instead puts the focus on human needs and understanding how they want to interact with systems and to improve their effectiveness and experience when doing so. So when it comes to human-centered AI, it's really important to define which humans. And like our earlier keynote mentioned, which I really appreciated, all machine learning is interactive machine learning. So many different humans can be the human in the loop. This could be model developers, other company stakeholders, end users who have little to no prior AI knowledge who are using these systems or need to follow recommendations. And most of who I'll discuss today is the end users who are not machine learning experts. So they might have, or they typically have some domain expertise that we want to incorporate back into the system, but they don't understand at least at the start of their interaction, how the system works. So when I talk about designing for the human in the loop, in my opinion, there are kind of two primary research goals we should focus on. So the first is understanding user expectations and experience when they're assessing and interacting with machine learning. And this is so we can build more effective ML-infused systems for augmenting humans' tasks and workflows. And by effective, we mean measurable improvements to appropriate trust, task performance, and user experience, and so on. So I'm now going to walk through a long-running research project that my group's been working on, where we first follow this human-centered design process to develop an interactive topic modeling system for non-machine learning experts. And interactive topic modeling is both transparent and interactive. So meaning users can see almost immediately what happens to their input. I'll get into this a little bit more later, but we use this system to explore user interaction and experience with a focus on user reactions to unpredictable model updates. Okay, so a little background on topic modeling. A fairly common application in machine learning, specifically natural language processing, is being able to process large amounts of unstructured text. And this problem exists in a number of domains, like a legal team that needs to identify information of interest during discovery phase of their research, and they just have tons and tons of documents to go through, or perhaps a customer service department who wants to know the common types of things people are complaining about for their company. And one technique that we can use for making sense of all this unstructured text is topic modeling. So topic modeling is a common approach for modeling text without predefined labels. So it's unsupervised, meaning we have all these documents, but we don't have any labels that we're going to use to help classify it or categorize them by. So instead, topic modeling takes a collection of documents and discovers the topics or themes that the documents are about. So you can imagine you have this corpus of documents, these news articles that are about sports, crime, and technology. And within these documents, there are groups of words that appear together more or less frequently, which are discovered as topics. So for example, the words base and run will appear in documents about the topic of baseball. The words Apple and device will appear in documents discussing the iPhone. And documents are also typically about multiple topics. So unlike in a text classification where we assign one class to a document, topic modeling takes advantage of the fact that really documents talk about multiple different topics in different amounts or proportions. So a document might be 60% about the iPhone and 30% that there is an expected announcement for it, and so on. And topic modeling captures this intuition by modeling each document as a distribution of the topics, and each topic is a distribution of words from the vocabulary. And once you actually start trying to use topic modeling for real use cases, it's pretty clear that topic models are rarely perfect. There can be low quality topics or topics that don't align well with end users' understanding of the data. They can be either too specific or too generic. So what can we do about this? So first, let's understand at a high level how topic modeling is performed. So this plate diagram represents latent Dirichlet allocation, or LDA, which is a very common topic modeling algorithm. In reality, we only observe documents. All other hidden variables, including the topics, the topic assignments for the words, and the topic proportions for the documents, are inferred during modeling. And to influence this kind of modeling process, an algorithm expert can tune some of these parameters. They can specify the number of topics or add some useless words to a global stop words list, meaning they'll be ignored during modeling. And it can take many iterations of this sort of tuning by system developers before ending with a high quality topic model. But what about non-expert end users? We don't expect them to understand enough about LDA to effectively tune parameters or change the number of topics for their model, but they do have domain and general knowledge that we want them to be able to incorporate. So a solution to this is interactive topic modeling, in which users can inject domain knowledge to guide the model generation, such as by modifying words, topics, or documents. So for example, suppose we have this baseball topic. A user might want to add additional baseball words like out and inning, as well as move the word baseball to have the highest weight for the topic. And users can perform this interactive refinement until the model is high enough quality or better matches their expectations for the data. And for our research, we wanted to build an interactive topic modeling system, but we also importantly took a human-centered approach. So we first studied how users want to interact with topic models without biasing them by what is possible in existing systems or algorithms. So to do this, we took a static topic model of 20 topics from New York Times corpus. We showed that to a set of 10 users who are non-machine learning experts, and we ask them to look over the topics and describe if and how they would like to refine them. And users said things like, I'm annoyed by common words that don't help me understand the theme, or I want to remove documents that are about insurance. So we then perform qualitative coding of these statements to identify the different refinement types that are described by users. So they want to be able to remove words or reweight or emphasize words or remove documents from the model. And then this analysis gives us a set of user preferred refinements, including adding, removing, and reweighting words, removing documents, splitting and merging topics, and then also ignoring words from modeling altogether. And since no prior interactive topic modeling system has implemented this full set of user desired refinements, we developed our own implementation using LDA with Gibbs sampling. And my goal here is not to tutorialize LDA-based ITM, but I do want to provide a kind of cursory understanding of how user feedback is incorporated. So very generally, we treat our refinements as users correcting model errors. So every time we get a refinement, we need to do two things. We need to forget things that the model has learned and inject new knowledge into the model. So when we forget, we strategically unassign or reset topic word assignments to -1 and then decrement the associated counts with those tokens. So we make it as if the model has never seen that word before in modeling. And then when we inject, we provide hints that encourage the algorithm to make better decisions going forward. So we do this by modifying alpha or the document prior and beta the topic prior. And importantly, we use a vector or asymmetric form of these priors instead of the scalar, which means we can modify the priors at the word, topic, or document level. So we can increase or decrease the prior for words that we want based on how we want the model to incorporate them. So if we add a word, we can put a really high prior for that word for the topic, so the model is more likely to learn that word for the topic. Okay, so any additional details beyond that, I'll refer you to the paper. But we implemented these 7 refinements on top of latent geospatial allocation, and then we developed a simple web app for our system. So here we're showing a topic model of 10 topics for tweets that are complaints about various airlines. On the left side of the system is our topic list. Each topic is listed with the topic number and the first 3 words of the topic. And then on the right is the full topic panel. Here, the first topic is selected, and we show the top 20 words and top 40 documents for this topic. So this one appears to be about checking a bag, and you can see words like bag, check, and specifically, a lot of these are about United. So users can then perform implemented refinements using simple interactive mechanisms. So they can click X to remove words or documents. They can click in this input area and type a new word to add it. They can merge or split topics by interacting with the system as well. So now that we have this ITM system, which is based on how users want to assess and improve models, we want to understand users' experience with it and perhaps what that can tell us about human machine learning interaction more generally. So importantly, ITM provides this interactive machine learning scenario where feedback is easy to validate and updates are unpredictable, or they can be unpredictable. So what do we mean by that? First, what do we mean by unpredictable updates in ITM? So interactive topic modeling, like most interactive machine learning techniques, must balance user inputs and faithfully modeling the underlying data. So this means that systems sometimes incorporate user input in unexpected or unpredictable ways. In topic modeling, there are kind of 2 types of unpredictable updates that we think about. First, a user's changes to the model are not always incorporated as specified. We call this adherence or a lack of adherence. And then small changes to a topic model can also propagate in unexpected ways. So we can call this model instability. And to demonstrate this, remember in our earlier example that we had a user who added the words inning and out and moved baseball to be the first position of the baseball topic, but our resulting topic might not be exactly as that user had expected. So we could see that strike, another baseball word, was added to the topic, which now no longer contains the word coach. You can also see that baseball shows up in the second position instead of the first, as the user had specified. And on the other hand, what do we mean about controls in interactive topic modeling being easy to validate? So interactive topic modeling is a little different than what we normally think of for interactive machine learning. So in a typical interactive machine learning, like supervised scenario, user provides input in the form of labels, preferences, or perhaps some simple features. And then the model updates and produces some new output. And this repeats either until the user is done interacting with the system or the model has reached some desired accuracy or so on. And here, users don't really get any insight into how the model incorporates their feedback. So they might see new labels or get additional music recommendations. Hopefully, the model appears to be improving. But in this case, controls are difficult to validate. Users don't get much insight into whether their feedback is incorporated at all, predictably, or as they expect. And it turns out that for difficult to validate controls, it sometimes doesn't really matter to users what the system is doing or whether it's doing anything at all. So take, for example, this article about dummy AC thermostats. So this article goes on to estimate that perhaps 90% of office thermostats are fake, yet people are happy nonetheless just with the illusion of control over their office temperature. And similarly, prior work in machine learning has explored control settings for reordering Twitter feeds, which is a difficult to validate case. So in this example, some users received working controls that updated their news feed by popularity, where others received non-working controls, which just randomized their news feed when they use them. And in this work, they found that users didn't notice whether that the controls weren't working, that some were just displaying random tweets. Instead, across the board, they had positive experience and they wanted these controls, whether they actually worked. So prior work in interactive machine learning typically focuses on user control simply in terms of whether or how users provide model feedback, and less focus is on humans' perceptions and their reactions of what is done with that feedback. So interactive topic modeling provides this interesting case where controls are inherently transparent, users interact with the model representation, and therefore easy to validate. They can immediately see what the model does with their input, but these controls can also be unpredictable. So compared to the opaque systems where providing controls, whether or not they work, seems to increase satisfaction, we're interested in whether users perceive unpredictable controls in interactive topic modeling and how that affects their experiences and interactions with the system. So what do? We perform an interview study with 12 participants using our system to organize a Twitter data set. And these studies explored experience with interactive topic modeling in general, with perceptions of various system characteristics like latency, update quality, and so on. But I'm focusing specifically on whether users notice and their reactions to unpredictable controls. And in this, in the system, they organize a Twitter data set for airline complaints, and they're told that it's for the purpose of writing a blog post. So for this task, we use a Kaggle data set from the Twitter US airline sentiment data set, which contains about 15,000 tweets from February 2015, which are directed at 6 popular US airline companies. And these tweets were manually labeled as having positive, negative, or neutral sentiment. Of these, 9,000 have negative sentiment. You can see a sample of those here. They describe different types of complaints, like being on hold and flight delays. And for these airline complaint tweets, we generate an initial topic model with 10 topics. Here's a sample of those. As you can see, some of them are fairly coherent. Topic 4 appears to be about lost baggage. Topic 9 appears to be about customer service. Others are a little harder to interpret, like topic 5 contains some HTML tokens and other random words. And this first kind of exploratory study we performed included 12 non-expert participants, which were recruited from campus mailing lists. They were given a 10-minute introduction to the system on a separate model where the interviewer described each refinement and asked them to practice the operations using the tool. They then reviewed the raw tweets of the data set and were told that to imagine that they've been asked to organize these tweets into different classes of complaints because they're going to write a blog post about common complaints that people have when flying. And then they open the system. They're instructed that the system has provided them with an initial model of 10 topics to help them summarize the tweets, but it might have some flaws that they can refine using the tools. And they're asked to talk aloud while they do this. And afterwards, they complete a post-test survey, or they're asked things like whether they noticed adherence or instability and about other system characteristics. So what do we find? So participants rated their agreement with statements about unpredictable controls. So for adherence, the majority of participants seem to agree with the statement that the refinements I made were applied as expected when I clicked update. So in general, users felt the system adhered to their input, but some were kind of more to the middle in that they noticed lack of adherence. And then in terms of stability, there's quite mixed agreement with the statement, no changes other than the refinements I made occurred when I clicked update. So some participants noticed it a lot, others not at all, this kind of model instability. Then we dig into users' reactions to unpredictable control. So we did an interview study, so we're able to kind of discuss their reactions. There was lots of thinking aloud, so we get a lot of interesting insights. And surprisingly, we saw both positive and negative reactions when it comes to unpredictability. So first, for the case when the system did not make a change exactly as the user had specified, or there was this lack of adherence, this participant was frustrated because the change word order operation was uncontrollable for them. But in another case where the system actually adhered to the input, so for example, a participant added words to a topic which were given high priority to the topic, she noted that, oh, well, she could actually be wrong. The system should have some leeway. So in this case, she didn't prefer sort of full control or adherence. Then there's other cases where the system made other changes than specified or showed some instability. So on the positive side, a participant described instability as making the model better. But on the negative side, one participant described a scenario where they were happy with the topic until an update changed it, and then that made them unhappy. So while these negative reactions to unpredictable updates are no surprise, the negative reactions to predictable updates and positive reactions to unpredictable updates are a little more interesting. And from these, it appears that reactions to unpredictability can be affected by things like confidence, trust, and model update quality. So in this case, the participant had a positive reaction for what they thought was a high quality update and made the model better. But on the other hand, in this case, participant wanted less predictability because she wasn't sure of her added words, or she had low confidence in her input. And we also observed some other cases where participants showed either low confidence in themselves for the task, like they didn't want to use the remove document refinement, or they showed high trust in the model, like saying, well, if the model contains certain topics and words, then it must be for a reason. So to summarize from this interview study, while prior work focuses primarily on whether or how users can provide feedback to models, we look at how models incorporate that feedback and participants' reactions. So participants seem to notice instability more than lack of adherence. They had both positive and negative reactions to unpredictable controls in general. In some cases, less confident participants desired less adherence to their feedback, and participants were okay with instability when the system updated well. So from here, we wanted to dig into control a bit more and explore these concepts with more participants and also with different modeling approaches. So we perform a controlled study with 100 participants. We use the same task of organizing airline complaints for a blog post, slightly updated system. And again, we are looking at instability and adherence primarily, but other kind of interactions as well. And we're also compare 3 different model update approaches. So we compare these 3 distinct modeling update approaches for refinements, which vary in how input is incorporated. So we either use priors, like in the previous study I talked about, or we use constraints, and then how inference is performed. So we either use variational inference or Gibbs sampling, which was from the prior study. And again, recall that in interactive topic modeling, we incorporate feedback by first forgetting the previous incorrect information learned by the model, and then injecting new information based on feedback. So the approaches we use vary by inference technique, either Gibbs sampling or variational inference, and this handles how information is forgotten. And they also vary by feedback technique, which is either priors or constraints, which handles how information is injected or the hints that we give to the model. And we choose these approaches because they differ in attributes we're interested in exploring. So in our study, variational inference provided more stability than Gibbs. Informed priors provided higher adherence than constraints. And then in terms of latency, informed priors with Gibbs provide the fastest updates for our study settings, but unfortunately all our implementations were quite slow, taking 15 to 20 seconds per refinement, which is not acceptable, in my opinion, for interactive machine learning. So that did seem to affect some of our results, but I'll get to that later. And we're really interested in whether users notice differences in adherence and instability between these modeling approaches and their reactions to it. So we implement a similar system and interface from the previous study. We make some enhancements based on user feedback from iterating from the last round. So we had 3 new refinements that were desired, being able to create new topics, delete topics, and rename topics. We also support an undo functionality. And for this study, we recruited 100 participants on Upwork platform. So for the purpose of our study, we had a pretty in-depth task. We use Upwork instead of Mechanical Turk to get more motivated users who will spend longer with our system. We randomly assign each participant to one of 3 modeling approaches, and each participant gets a unique model of 10 topics for the airline complaints dataset. They then perform a guided tutorial of the different refinement implementations and are given the same task and interface from the previous study. They're asked to refine the model to organize the tweets into different types of air travel complaints for the purpose of their blog posts. They're given 30 minutes to do this. And afterwards, they respond to closed and open-ended questions on their perceptions and experience with the system. So this includes what they most liked and disliked, what was unexpected. We also tracked their interactions, so which refinements they used, and so on. So first, we explore whether users perceive a lack of adherence. So from the subjective responses, participants responded to the tool made the changes I asked it to make. And in general, they thought the 3 systems adhere to their input. So users in the constraints with sampling condition did give significantly lower responses for adherence, which aligns with the objective adherence measured for constraints with Gibbs sampling, which had lower computed adherence. So we did find that it appears they could notice that this system had less adherence than the others. And recall that in prior work, we found that users, prior work found that users didn't really seem to notice or care what happened to their input in the case when controls were difficult to validate. But in this study, where users could observe how their refinements affected the model, we found that this kind of lack of adherence was the second most disliked characteristic of the system, behind only the really slow updates. And it was the most unexpected characteristic of the system. And we also found that refinements that did not work as expected, like specifically, these were the change word order. So being able to reweight the word, it was kind of the least controllable refinement. Add word also had less control than some others. These were less popular. Both subjectively, participants said they liked these refinements less, but also objectively, they used these refinements far less than the others in their interactions. So these findings further demonstrate kind of this importance of considering adherence for systems where controls are easy to validate. So when users can immediately see what happens with their input, they're easily frustrated by things not working as expected. So now looking at instability. So here participants respond to the tool made other changes beyond what I asked it to make. Again, as in our previous study, they're pretty mixed on whether they noticed this instability. And while one of our models had significantly higher computed stability than the other conditions, the perceived instability was not significantly impacted. So it was kind of just mixed on whether they noticed this at all. And again, participants seem pretty polarized by instability. So for example, one participant said, well, they didn't expect the words to update after adding a new one, but they thought this was cool. Another said, I removed a word and I saw it in a later topic. This is bad machine learning. So these findings suggest that users might be willing to share control when models update with high quality or what they consider to be reasonable changes. So to summarize the study, participants disliked the lack of adherence, second most behind only slow updates. Instability was polarizing. Some participants liked it when it surfaced interesting information, others did not. In general, participants preferred the more controllable refinements. Those were used more frequently. And across the approaches, they differed only in whether they noticed adherence. So what do these studies and kind of prior work tell us about better design for the human in the loop at the intersection of transparency and control? So first, the human-centered design focus is important. We should design for what humans need, their existing workflows, and how they want to interact with systems, not algorithm constraints. Also, users want to be heard, but they might be willing to share control with a good teammate. So users want and need to be in control, but machine learning systems sometimes must balance user inputs as well as faithfully modeling the data, which means this sort of shared control or machine agency is necessary. And users might be willing to share control, like in our studies, where these unpredictable controls were more accepted when the system made high quality or reasonable updates. And then similarly, our findings stress that not all input is equal, or more that not all users expect models to treat their input the same. And this is probably especially likely in these subjective or more complicated interactions of interactive topic modeling. But some humans were more confident or more sure of their input. They wanted the models to adhere fully to their updates, where others wanted the model to have some leeway with what it did with their input. And so to this end is even more control needed. Should users have a way to express not only their input, but more about how the model should incorporate it? Or should models infer this adherence in some way, infer how to update with user input? So just want to briefly touch on future work in human AI interaction that is interesting to me, but some research directions for a slightly different paradigm from interactive topic modeling, specifically active learning with the human in the loop. So I don't think I need to go through over this, but I will quickly. Very generally in active learning, we can start with some initial model. So perhaps we have some large generic language model. We use it to perform a labeling task. From there, we determine the uncertainty of our labels. We can prioritize those examples that we'd like human input on based on the ones the model is most uncertain about. And then we can ask some human domain expert to provide those labels, and then we retrain. And so this active learning pipeline uses model uncertainty to prioritize the labeling tasks for human domain experts. And this use case, in my opinion, motivates some interesting research directions. So the first is accounting for users' uncertainty in their input. So in many interactive machine learning or human in the loop contexts, so thinking like the dual list example of interactive text classification, we tend to treat user input as fairly certain, as like additional training labels, ground truth that we can train on. I know this is not the case when we're crowdsourcing, but for more kind of like human in the loop iterative context, it is. So, but it's not always the case that input is certain. So particularly when users perform more complicated or subjective tasks or interact with complex systems like in interactive topic modeling, or in these active learning contexts where we're asking for input on particularly hard or complicated examples, this can be problematic because users might be frustrated, or they might lack confidence in providing input without the ability to specify that uncertainty. And we could also be training on incorrect input if we're not accounting for that uncertainty, which could lead to reduced system quality. So we have some ongoing research that is exploring whether asking users to specify their input uncertainty and then accounting for it when updating a classifier leads to more accurate models and a better user experience. But this is definitely an interesting area, I think, that we should be pursuing. And then kind of second area around active learning is user-oriented active learning. So trying to choose examples or input requested based not just on what is most useful for the algorithm, but also considering users' experience and their skills. So for example, some domain experts might be better at providing certain types of input or labeling particular examples. And another facet of this is related to context switching. So labelers might be better at labeling topically similar examples or labels that are in kind of a similar context to what they've been working on. So there's been some initial work in this area by some of my collaborators and others, but most of this has put less focus on end users than kind of the algorithm implementation. So it'd be interesting to explore here, perhaps user studies that compare different user-oriented active learning strategies to see with which users prefer, users can best label, and which are best for models. And then we might consider further personalized active learning strategies where users label based on their expertise or which types of samples they're best at labeling. All right, so with that, I just want to acknowledge all of the hard work of my collaborators on these different projects I discussed. If you're interested in any of the avatars that I have in my slides, there's a link to those as well at Diversity Avatars. And I will leave you with my favorite XKCD comic on human AI interaction. And thank you.
Thank you very much, Alison. So we are now open for questions, and I should advise the questioners that the recording is in progress. So your question will also be recorded. So questions from the audience, please. The best would be to raise your hand that we see that there's a question, and then you get the word. So do we see some raised hands? So meanwhile, maybe I make the icebreaker question, because you know the people are shy, mostly they're shy. So Alison, I really like your approach. It was very refreshing. And I understood that these informed prior models provide an effective way to incorporate diverse feedback into these topic models from Bly et al. And to improve this user control and the topic coherence. Okay, so my question would now be, how do you think should future work compare the systems with end users and compare with your particular method? So would you have some envisions here?
Yeah, so you mean systems that are based on different kind of update techniques?
Exactly.
Yeah, that's a great point. So we did the comparative study where if it's possible to compare with the same exact kind of front-end interaction, then you can replace the modeling behind the scenes and let users interact and gauge their perceptions. And for example, one thing that was interesting to objectively explore was which refinements they used, because in some cases, the refinements of some of our models didn't work as well as others, and we could sort of see that users tended to stray away from refinements that didn't work as they expect. If this worked because we implemented these different systems with the same exact set of refinements and the same front-end system, which made it easy to compare just the modeling approach. It gets harder the more, as you know, in controlled studies, the more different things that you have going on. If we don't support the same refinements or the same visual way of interacting, we have to get a little more creative in how we explore. And in that case, probably comparing within subjects, and then more of an interview might be the better way. But yeah, that is one of the hard parts when we talk about comparing these systems, because most of these systems have been implemented quite differently, and there's many decision points to make, not just how input is incorporated, but also how input is provided, how the model is visualized. So it gets quite complicated.
Super, Alison. So meanwhile, we have a question. So George Foreman raised his hand textually. So George, please show yourself and please ask your question.
Oh dear, I have to show myself. Well, Alison, this is it's very interesting work. I never would have thought of doing a study like this. So you found that a few people were actually positive when the computer didn't do what it was told, thinking, well, maybe it's got good reasons for that in the modeling. But I hypothesize that's because they hadn't worked with it very long. If you worked with a tool for a long time, you realize how little control you have and how frustrating that is. So what I want to ask you is, in your heart, how strong do you believe this effect is? You know what I mean?
Yes, I do know what you mean. Okay, I do agree that had they worked with it longer, we would have seen certainly much more frustrated people. The people who were already getting frustrated when things weren't working as expected would probably just abandon the model, to be honest. But there were people who were kind of asking for more of this sort of teaming feel. They wanted to work with the system. I provide my input, and then I don't see exactly what I expect, but I expect to not see what I expect. I expect to see kind of this kind of, here's my hint. It's almost is more of like, here's my suggestion. What does the model then think makes the most sense for the update? And in some ways, it seems to be based on kind of just the confidence or the background for how much we've explained to them the machine learning, or they've learned about it. But I think it can just be sort of almost a personality trait where some people are like, this is what I want to see, and this is how I want it to work. And for whatever prior experience they have, they expect, HCI guidelines tell us that systems should do exactly what they're told, and there's no room for difference there. But others just did seem to feel more comfortable with this sort of teaming relationship. So I feel like it's not all bad.
Sure. Well, you showed that cluster of all those HTML tags and stuff like that. And I developed a clustering tool that was used at HP and customer support for years. And they were always like trying to tweak it, and they couldn't get control over it. It was very frustrating for them. If you get rid of that cluster, then those terms appear in all the other clusters. And I think part of the issue is what they're trying to control is so complex. It's not just a list of stop words. It's way more complex.
Yes, I agree. And I think part of that is also in our system, we expose this is the model. These are the words, these are the documents, here's what we can provide to you. But there are levels of abstraction that are probably more appropriate for what people actually want to do. If it's just an organizational tool, then a folder structure where you're dragging documents around and there's a topic model under the hood. But they don't need to know exactly about that. Maybe it's a folder structure where we show the top few words of the topic, so we're still getting that part. And they can move documents, they can delete documents, they can change words for the folder name, and that level might be the appropriate abstraction, which would kind of hide some of the kind of messiness, but also give them more of the interactions they probably desire.
Thanks.
Thank you very much, George. Yeah, we have another question from Vincent. So Vincent, would you like to ask your question verbally, or should I read it?
I can do it.
Okay, super, thanks.
My question is related to the previous one. What is your idea to add or to incorporate novelty in the loop? We had an whole term which was visual data mining. That means that if I'm faced to a particular data set, I would like to visualize the information, accept that my visualization is not the same as your visualization. And the idea is to incorporate novelty as a way to visualize the data. And the second part of the question, how it could be acceptable for people who decide after if this visualization is good or not.
Yeah, so making sure I understand the question, do you mean novelty in the fact that each user is different in how they want the model to look, or novelty in the fact that we want to see something that's not actually in the underlying data?
In fact, both, because I would like that each user could visualize by his way a particular knowledge about data, and also that could be interesting to add novelty in this process to allow to not have the same point of view.
Yeah, okay, that's really interesting. Yeah, so as far as novelty in each user being different, that kind of is one of the benefits of interactive topic modeling is you can push the model in any way. So even topic modeling on itself is pretty, depending on how you seed your algorithm, is pretty unstable. Every time you run it, you'll get a different model unless you set it up in certain ways. And this is kind of because of how the model sort of randomly seeds and then learns the patterns. So by doing that, each user can then you can have many distinct starting models. Each user can have a starting model and sort of guide it in whatever direction they want it to go. So it does, oops, sorry. Okay, so it does kind of allow for that level of novelty, although there's tons of scale issues when you talk about if you actually want to have many, many different model representations depending on your system.
There's also a PDF version if you prefer right next to it on that page.
Sorry, I heard someone else. Okay, but then as far as the novelty in something that's not in the data that's underneath that's being modeled, that's the harder part. So how these models are implemented now, they can only listen to the user so much as is kind of allowed by the data. For example, we had plenty of users who tried to add words to the topics that were not in the vocabulary. The model cannot do that with how it's currently implemented. It can't just make a new word and add kind of counts to it. That's something we could support in the future, but that is something we need to get more into, is how much should we let the user control in a way that doesn't actually match with the data that they're trying to model.
Right, but at the end, you have different point of view, and the question is how is acceptable, because you are not in the right box. That could be have been imagined by somebody else. So you define your own model, your own visualization, and to measure this kind of results.
Yeah, it's interesting too, because when we talk about evaluating these models, because they're so subjective and we want them to match users' understanding of the data, that different users evaluate differently because different users feel like the data should be organized and visualized in different ways. So interactive topic modeling is a way to let users kind of individually personalize the models to how they want the data to be represented, what they want the patterns to look like.
Thank you.
Yeah, thank you very much. Merci beaucoup, Vincent. So we are perfectly on time. So the role of the moderator is to keep time. So I didn't need anything to do. So Alison is the perfect speaker. Thank you very much. So